Right, so welcome, Oxford Philosophy of Physics. My name is Simon Saunders. It's a great pleasure today to welcome Wayne Myrvold, our speaker, who's going to speak about subjectivists about quantum probabilities, that you should be realists about quantum states. Wayne's work has is well known to us. He's made important contributions to both the Everett interpretation and collapse theories. Most of his work has been in the foundations of statistical mechanics, thermodynamics, and quantum mechanics. But also in philosophy of science. I think Wayne's heroes are mine too, Abner Shimoni and Howard Stein. So we share that. We also shared an existence when I was at Harvard and Wayne was at BU, the very happy times, and Wayne has been a visitor to Oxford on several occasions. Wayne, it's such a pleasure to have you here. The floor is yours.
Thank you, Simon. Thank you for inviting me, and thank you everyone for coming. Yeah, so it's good to be as having spent some time there, as Simon mentioned. I just got a little message saying that my internet connection is unstable. So hopefully it'll hold out for the duration of this. But if I disappear, then I'll just try to reconnect as quickly as possible. Yeah, so the title of the paper is Subjectivists about Quantum Probabilities Should Be Realists About Quantum States. The talk is based on a paper of mine of the same title, which came out last year in this book, dedicated to the work and influence of Itamar Potowsky, another philosopher that I admire. If you're not familiar with this book, it's got a lot of really good stuff in it, and I suggest that you check it out. And that in turn was a sequel to another paper which came out in this book also last year, which is also a nice book. And what happened is I was working on this, that there was a section giving sort of the technical details that kind of got out of hand. So it got hived off into a little paper in PRA. So the background to my thought about this basically stems from, I think it was probably about 20 years ago that I first met Chris Fuchs and Rob Speckens. Speckens was a graduate student at the time. And over the years, I've had a number of discussions with them and trying to understand what they think and why, and also to persuade them that they shouldn't be thinking this. So some of you will be familiar with these names and the term Cubism. Some of you won't be. Cubism, for quantum Bayesianism, is a term coined by Chris Fuchs. He takes the word Bayesian to mean not only a position that countenance subjective probability, but one that rejects any kind of a notion of objective probability. And it's kind of unfortunate that among physicists, due to the partly to his influence, people have taken the word Bayesian to mean a rejection of objective probability, even though that has not been traditionally part of the idea. And so basically, well, we'll talk about the tenets of Cubism in a little bit, but it's the idea that probabilities in quantum mechanics are subjective probabilities, and they're probabilities that an agent uses to set her degrees of belief or credences about her own future experiences. And it's a mistake, according to them, to think of quantum mechanics as a physical theory in the traditional sense of telling us something about the world independent of us. Rob Speckens, someone who's been influenced by Fuchs, but isn't necessarily an adherent to the same kind of views, has been defending a view on which quantum states don't refer to anything in reality, but are epistemic in some sense. And so my experience with this is I have these discussions with these people, and these are all very, very smart people who I respect quite a bit. And I find them saying things that I find it difficult to credit. I'm really going like, do you really believe what you're saying? Because sometimes these positions sound literally incredible. And if you're not familiar with it, you'll see some quotations from Fuchs later on. By the way, I think that one thing that's become clear to me is that Cubism is not a single view. There's either many versions of it or there's none. And in particular, when you talk to Rudiger Schack and when you talk to Chris Fuchs, you will, even though they co-write papers together and co-write manifestos for Cubism, they will say different things in response to certain kinds of questions. Okay. Now, I think that realism about quantum states, the idea that distinctions between pure quantum states correspond to physical distinctions in the world, that this follows from assumptions about the world that they either do believe, even if they don't explicitly avow them in their published papers, or that they should believe in the sense that, well, I'll explain why in a bit, what I mean by they should believe these things. And, but the basic idea is that there are assumptions that are not particularly quantum and not particularly classical, but are they're deeply embedded in the way that we deal with the world, both within and outside of science. Now, of course, we don't want to be dogmatic about anything at all. That's one thing I learned from my my teacher, Abner Shimoni. But so if we should be in a position that no matter what kind of assumption we have about the world, we should be willing to question it or abandon it given evidence of its falsity. But I don't think that the sort of empirical evidence that we have, the experiments we use quantum mechanics to deal with, gives us any reason whatsoever to doubt these assumptions. Okay. And the interesting thing is that the argument I'm going to give in favor of the claim that we ought to be realists about quantum states actually doesn't violate the fundamental precepts of Tenets that you'll see in various manifestos of quantum Bayesian. So, it violates a sometimes unspoken prohibition on our theorizing about the world that isn't always explicit in these statements of Bayesianism. So if you don't know what I'm talking about yet, this will become clear. Okay. And before we begin, I just want to make clear what kind of question I'm addressing. The question that I'll be addressing here, and this is a question that has motivated pretty much all of my work in philosophy of quantum mechanics, is what, if anything, does the empirical success of quantum theory tell us about the world we live in, the physical world? There's a question I won't be addressing, which is the question of whether Cubism gives rise to a research program that's a fruitful source of conjectures, introducing research problems, etc. And the reason I want to distinguish this explicitly at the outset is as my experience in having these conversations I was talking about, particularly with Chris Fuchs, but also sometimes with Robin Speckens, is you can be talking away and think you're starting to get somewhere, and then Fuchs will say something like, well, in the end, for me, I'm going to judge an interpretation of quantum mechanics by its fruitfulness for giving rise to interesting research questions. And for me as a philosopher, I sort of stop and say, well, hold on, wait. Okay, if that's relevant, then we weren't talking about what I thought we were talking about. And I think there's a sort of sociological difference going on here. If you're a physicist, it's your job, if you're a theoretical physicist, it's your job to publish papers in physics journals. So, proves theorems, get results, the sort of thing that's publishable. And it's not your job to step back and just talk about the philosophical implications of these things. your work might be motivated by philosophical views, and you might draw philosophical implications from your work, but publishing things in philosophy journals isn't your job. And what these people that I've mentioned on the previous slide have done is they've adopted a career path, a certain research program surrounding these sorts of questions, and it's been good for them. There's been a string of papers, and I think that colors sort of the conversations, because that involves more than just a certain belief about the way the world is, but being a member of a certain community and promoter of a research program, lobbying for funding for these things. And it sort of becomes a little bit like being a supporter of a football team, for example. If you're watching a football game and you're with a bunch of fellow fans and rooting for the outcome of the game, what you're not supposed to do, in fact, it's a faux pas to pause and say, well, if we evaluate the evidence, it's probably likely that our team isn't going to win. So anyways, I just want to make clear that I have no problem with people pursuing this as a research program, and there's been interesting papers and stuff like that, but that's just not the question that I'm addressing in this. Okay, so what I'm going to argue for is there are certain results in the literature that sometimes get called psi-ontology results about the realism of quantum states. Probably the best known of that is the Pbr Theorem, Pusey, Barrett, and Rudolph. The paper that I mentioned on the first slide is my modification of it. There's another interesting theorem by Barrett, Cavalcanti, Lal, and Moroni. My claim is that these theorems go through, even if all the probabilities invoked to them are taken to be purely subjective probabilities, degrees of belief of some agents, as long as you modify the conclusions. So what I want to argue for is that in agents whose credences about outcomes of experiments can be represented by quantum states, should believe that preparation procedures with which she associates distinct pure quantum states produce distinct physical states. And when I say what she associates distinct pure quantum states is that those states represent the Born rule probabilities given by those states represent her degrees of belief about degrees of belief about outcomes of experiments on a system that's been subject to that preparation procedure. Okay. But before we even start talking about quantum mechanics, I just want to step back and advance some considerations which I regard as sort of pre-theoretical, the sort of thing that we bring to our theorizing about the world. A lot of this work has been inspired by quantum information theory, so I just want to just sort of talk about communication in general. So a very basic schema of communication is that one agent, Alice, wants to convey a message either to another agent or to her future self, maybe as an aid to memory. The reason for that qualification is that the official Cubist line is that agents are supposed to use quantum mechanics to set their credences about their own future experiences and not make predictions about what other agents are going to experience. So I'm going to call the agents who are engaged in this communication Alice and Bob as the sender and receiver. But just bear in mind that for all we care, those could be two names that Alice goes by. Alice and Bob could be the same person. Okay. So in order for this to be informative, there must be two or more alternative messages you can choose between. So we assume that she's got some device on which she can perform alternative operations. I suggest as we're talking throughout, imagine you've got a laptop in front of you and you're taking notes. In the paper, I talked about taking notes on a laptop. And the reason I had that in mind is I'd given a talk a few months earlier at Perimeter Institute, and Rudiger Schack was in the audience, and I noticed he was indeed taking notes on a laptop. So this is something that Cubists have been observed to do. So imagine that the physical system is, a laptop, and the alternative operations that you're choosing between are choices of keystrokes. There's some kind of association set up between message and the operation performed. There's an element of convention associated with that. So Alice makes her choice, performs an operation, passes the system to Bob. I'm imagining that, like, you've got some physical system that you're sending to Bob, so a hard drive, just for convenience, or you hand the laptop to him. Nothing matter. It can also be you hit enter and you send a signal via email, however that goes. And Bob gets this thing and he performs a readout operations. So that could be displaying a message on the screen, or it could be a auditory readout. The idea is that there's going to be some perceptually distinguishable possible outcomes. And the whole point of this is that Bob learns something about Alice's early choice of operations. Right? Whether or not Alice and Bob are two different agents, or Alice is refreshing her memory about what she wrote the day before, something like that. Okay, so how to understand this? Why are they doing this? Well, I have noticed that people, and this includes Cubists, they tend to regard some physical systems as more suitable for the purpose of others. So I have seen Cubists taking notes on a laptop. I have never seen them taking notes, trying to use a cantaloupe for that kind of thing. But what's the difference between physical systems that are suitable for this communication purpose and those that are not? I think the usual assumption, again, this is, I think, the assumption that we bring to our physical theorizing about the world. So I don't think there's anything particularly classical or quantum about it, is that Alice's choice of operation has an effect on the physical state of the system used, which in turn has an effect on the result of Bob's readout. Okay. Now, of course, they could be wrong about this. And a reason I'm emphasizing this is that Cubists such as Fuchs very often emphasize that the world is not under obligation to conform to our credences. And this is true. In fact, we have all had probably had some kind of experience in which we thought that the keystrokes we were making were going to have a lasting effect on the system that we were operating on, and that we could find out about readout later. And that assumption failed because of some kind of catastrophic disk drive failure or something like that. So, they could be wrong about that. But since the conclusion I'm going to have is going to be about the agent's credences, I'm not going to at any point make any assumption whatsoever about how that physical system actually works that they're dealing with. Okay, suppose we want to start to make a physical theory of something like this. All right. A common assumption, and again, this could be disputed if we had reason to do so, is Alice's choice of in-Bob operation has an effect on Bob's readout only via an effect on the physical state of the device that they're using. Right. If you believe that a certain device can serve as means of discriminating with certainty between two input operations, on the usual assumptions, you should also believe that the set of physical states, you can consider the set of physical states that can result from one operation, and the set of physical states that can result from the other operation. Neither one needs to be a unique physical state, but they have no overlap, because you're going to get distinguishable readouts depending on which operation you did. And in jargon that we'll shortly use, it means that you should believe that readout distinguishable preparations have ontically distinct effects. Okay, if we're going to, what I'm going to do now in the next couple of slides is get a little bit more formal and start to formalize these pre-theoretic considerations. And the formalism I'm going to be using is based on the ontological models framework introduced by Harrigan and Speckens. But I think that the way to think about that is that they're basically formalizing the sort of reasoning that's common to both our everyday dealings with the world and pretty much an awful lot of science. So we're going to assume that Alice can consider and have credences conditional on various theories about a setup of that sort. So you might imagine, if you think that this laptop is capable of storing distinctions between messages, you might start to form a physical theory about what's going on inside that thing. Right. So any theory of that sort should involve some set of possible physical states. And I'm going to assume that she has what I'm going to call act outcome credences conditional on the theory tree. And I'm going to, for simplicity, imagine that she has precise credences about these things. If you, at the price of some complication, you could have these, you make it a little bit more realistic and have these credences be somewhat vague and represent them, for example, by some set of credence functions. But for simplicity, I'm going to imagine she has precise credences. All right, so just a notation, this is her, Alice's credence and result are conditional on preparation act phi and theory T. So her credence conditional on theory T and preparation act phi that the readout outcome will be R. So those are the act outcome credences. Also assume that since she thinks that the state of the system mediates the act and the outcome, that conditional on the theory for any element of the theory space of the theory, she has credences about possible readout outcomes conditional on the supposition that the physical state of the system is omega. All right. So we'll be considering those two. Okay. And the condition that she thinks that the effect of her choice of preparation is mediated by the effect of the state of the device is the condition that a specification of the state of the device screens off the earlier preparation. So once the device gets into a certain state, then there's certain, then that's what's relevant to future readouts, and that's how the choices of preparations affect the readouts and affect. So if two different operations result in the same internal state of the device, then conditional on the external state, should have the same degrees of belief, but in the outcome, independent. And also, we're going to assume that conditional on this theory that she has credences about the states that result from a given preparation act. So this would be her for any. So there's presumably, given a theory and the state space of the theory, there's going to be some set of measurable subsets of that theory that the sorts of things you can have credences about. And so this, for any such set, she's got a credence that the state ends up in that set conditional on the theory T and a given preparation. Okay. And the reason is that I'm throwing all this up is I want to get to this condition. So that's all the stuff I need to express this system is those act outcome credences that we talked about earlier, conditional on theory T, that they're an average over the state outcome credences averaged by her credences about what the state is. So that's an epistemic expectation value taken with respect to her credences. Okay. All right. Okay. Definition. So she takes the two acts to be readout distinguishable on a given theory if, for any possible outcome of the readout operation, that outcome either has credence 0 of getting that outcome on preparation phi, or credence 0 on preparation psi. And that's basically the condition, is that no matter what outcome she gets, she won't be left undecided about whether the preparation act was phi or psi, because any outcome will rule out, in her mind, at least one of them. Okay. All right. We'll say that she takes the effects of two preparation acts to be ontologically distinct if there's some subset of the theory of the state space such that she is certain that it's going to be in that subset on the assumption of preparation phi, and certain that it's not going to be in that subset on assumption of preparation psi. Okay, and the reason we had the apparatus on the previous page is that it follows in a fairly straightforward way from that, is that if she has credences conditional on some theory 3 that specified those conditions that we had on the previous page, then any two acts that she regards to be readout distinguishable, she should take to have ontologically distinct effects, which is just a long-winded way of expressing the informal considerations we started with. That, if you think that tomorrow you're going to be able to find out by looking at the screen of your laptop whether you wrote A or B, you probably think that writing those things today results in distinct internal states of the laptop. Okay. All right. So we're imagining a situation in which there's certain at least preparations that you can perform on some system, such that Alice's credences about the results of future experiments can be represented, given a preparation, can be represented by some quantum state. And we'll say, following Harrigan and Speckens, we'll say that Alice takes a theory to be psiontic if she takes every pair of preparations which she associates distinct pure quantum states to be ontologically distinct. So there's no presupposition from the outset that those pure quantum states have anything to do with physical reality. We're using them from the outset to represent her credences, but if her credence is conditional on a theory T, her credence is conditional on a theory T might be that such that if she associates different pure quantum states with different preparations, she also always takes the physical states that result from those preparations to be distinct. And that's what I'm going to be about quantum state realism. Distinctions between pure quantum states correspond to distinctions in reality. That's what is meant by the quantum state realism of the title. Okay. So the restraint that quantum Bayesians impose that any agent's outcome credence should be represented by some quantum state. Okay. So suppose there are two preparation acts such that Alice's credence is about the results of experiments are represented by two orthogonal quantum states. Orthogonal are read out distinguishable. There's some experiment, if they're orthogonal, whether they're pure or mixed states, there's some experiment that yields such that for each possible outcome experiment, one or the other of those states has probability 0 of giving that outcome. Right? Okay, so given the theorem on the other page, if her credences satisfies those conditions we had, conditional on some theory, then conditional on that theory, she should take preparation acts with which she associates orthogonal quantum states to be ontically distinct. This, by the way, strikes me as nothing groundbreaking or earth-shattering, and I just think that this is something that everyone ought to accept. All right. So, and just going back to the more homely example. So I made this slide yesterday. And as I was doing it yesterday, I believed that choices I made yesterday would be informative about what would be displayed on my screen and now on yours today. And I believe that those choices are made via their effect on the internal state of the computer. Again, I just want to emphasize I could be wrong about this. But if I were to become convinced that my choices of keystrokes on Wednesday made no difference to the internal state of the computer, I'd probably try to get it fixed or replace it, because I would then no longer think that my choices of keystrokes on Wednesday have any effect on what is displayed on Thursday. Okay, so the argument so far is that given those conditions as on Alice's credences, she should take preparations with which she associates distinct orthogonal quantum states to be ontically distinct. And what the Pbr theorem does is extends that to non-orthogonal pure states. Some of you are familiar with this theorem, some of you won't be. I'm going to talk about it using some terminology that Matt Leither in a very nice review article came out with. So that theorem depends on a further constraint on probability distributions, which is called the preparation independence postulate. And the idea is that when you have a pair of systems, it's possible to do independent for any pair of quantum states. So those for those systems, it's possible to do independent preparations in such a way that whatever the ontic state of the pair is, it can be represented as just a state of one and a state of the other. So it's in the Cartesian product of the two state spaces for the theories. So that's one part of the preparation independence postulate. And the other part is that then they're probabilistically independent. So it's the possibility of independent preparations that have results like this. It's not saying that everything that I would take as a state preparation of these two states has this feature, just so that somehow or another it's possible to do this in such a way that screens off the correlations between their ontic states. So there's two parts. One is a condition on the state space of the combined system that has to include states that are in this Cartesian product. And the other part is the no correlation assumptions, given the Cartesian product assumption that there are preparations like that to give you probabilistic and independence. Right? Okay, so their theorem, I'm not going to go through the details. But once you set it up and once you see how it works, there's a relatively straightforward argument. Clever of them to think of. I wouldn't have thought of the argument, but not hard to understand once you've got it. If you've got a theory that satisfies this thing, then any pair of distinct pure quantum states are ontically distinct. Okay. One thing I want to be clear about this, because I've run into some kinds of misunderstandings in the literature, is other than this Cartesian product assumption, there isn't any assumption about the structure of the state space. Right? Because sometimes you'll hear it say that these theorems have some kind of classicality or hidden variables assumption. And that's just not in there. So the state spaces could be purely quantum. They could be, they could be, sets of quantum states. They could be, just about anything, including things that no one has ever thought of before. So, for example, Richard Healy, in his contribution to that book on scientific realism and the quantum that I was mentioning earlier, he says something that suggests that on his pragmatist view, the theorems like this just don't apply. What he says is, for one who takes the pragmatist view that he's outlined, there's a meaningful story to be told about the values of various magnitudes and circumstances when the content of the claims about them is well enough defined. So under certain circumstances, magnitude claims of the sort that a certain physical magnitude is in a certain subset of the real line will have truth values. They won't always have truth values, and there won't be any circumstances in which there are simultaneous truth values for all conceivable physical magnitudes. But he says these magnitudes are not always well defined, so there's no ontic state space on which even one of them always has a precise value. That's fine. But if you think that there's no ontic state space in the sense we're using, that would be incorrect. And it seems to me that he's suggesting that there's no ontic state space of the sort invoked in the ontological models. But that's not right. A state space could just be a state specification could be a list of all statements of the form this physical magnitude is in this set for those for which those are true. And the state space could just be sets of such spaces. So he suggests that the theory doesn't admit gappy state spaces, doesn't apply to gappy state spaces like that, but it's fine. And I actually think that his pragmatist quantum mechanics is in fact a realist view on the in the sense that I'm using the phrase. And I don't think he disputes that, but there's just this misleading passage in this paper. Okay, now you can just recast the Pbr theorem is cast in terms of probabilities without any real commitment about the status of those probabilities. But suppose we take the probabilities that are invoked in the theorem in credence. Right? So suppose that for any quantum state, there's a preparation so that Alice's credence about outcomes of experiments match the probabilities of the better state. So that's something that's, I think, often an unspoken assumption of Cubism. Not only that should my credences conform to some quantum be representable by some quantum state, but for some quantum state, there's going to be some preparation such that my credences correspond to that quantum state. So suppose we make that assumption. Okay, so for any theory T such that the state spaces for a pair of systems includes quantum states, and her credences about the result of independent preparations of distinct quantum states are concentrated on those quantum states, product states. So she is certain, credence 1, that the state that of the joint system that arises is in that Cartesian product. And her credences are about the states of the two systems are probabilistically independent. Then just run through the theorem using Alice's credences about all the probabilities, and get the conclusion that she regards the effects of quantum state preparations. I'm sorry, that's a typo. Effects of the two preparations as ontically distinct. So her credences that any pair of quantum states are ontically distinct should be at least as high as her net credence in all such theories. So if she had credence, if she were dogmatic that quantum states, distinctions between quantum states do not correspond to distinctions in reality, then she would have to have credence 0 in the class of all such theories. Okay. One thing is that the idea of realism about quantum states here is fairly non-committal. Just the idea that distinctions between quantum states correspond to some distinction in physical reality. And that leaves very much open the question of what sort of thing a quantum state refers to. And particularly, there's no assumption that it's anything at all like anything in quantum classical physics. Some of you know that in some of the literature on the foundations of quantum mechanics, particularly those by the bone mechanics school, there's talk of the primitive ontology. They divide what's real according to the theory into primitive ontology and the rest. So for them, on on Bohmian mechanics or the Broglie-Rome pilot wave theory, the primitive ontology would be particle positions, and the quantum wave function plays a role akin to a physical law. That its role is to guide the dynamics of the primitive ontology. Okay, that as far as these theorems is concerned, and the people who talk about primitive ontology do not dispute this. Those are realist assumptions. And the reason I'm saying this is only because I've run into people who are under the impression that taking what they call a gnomic view of the quantum state means that these psi-ontology theorems don't apply to that view. And that's just not true. On such a view, there is a real distinction out there in the physical world, depending on what quantum state preparation you do. It's just not a distinction in the primitive ontology. Okay. All right. So one reason that I have for concern about the applicability in general of things like the Pbr theorem is that it does indeed include a constraint on the state space of the theory, this Cartesian product assumption. And my attitude is that if we're gonna take seriously the idea that we're really taking these theorems as giving us reason to believe that quantum states correspond to something in reality, then it ought to be the sort of thing that we expect the applicability to apply, not just given our own current theory, but it should be robust under extensions to successor theories. And we might worry about whether that's true. In fact, we might worry about whether it's true even in current quantum theories. Can you actually completely disentangle two systems? So, and if you can't completely disentangle two systems, if you can't exactly prepare a product state, if you can only approximate it, then the Cartesian product assumption fails, even in quantum theory. Okay, so what I wanted was a version of this that does without the Cartesian product assumption. And in that paper in Physical Review A that I mentioned, and it's also in my chapter for the scientific realism in the quantum book, I introduced what I called the preparation uninformativeness condition. I see there's a typo. It should be uninformativeness. So it's a dreadful phrase, but anyways, that's what it is. And basically it's supposed to compare systems subjected to independent preparations, each chosen independently from some pair of preparations. So it could be phi and phi or phi and psi, any of the four combinations. Right. And suppose that you've got conditional credences, conditional on any hypothesis about the state of the composite system, about which preparations were done. And in particular, conditional on a complete specification of the state of the composite system. If I tell you what the state of the composite system is, that might or might not be informative about what preparations were done. So you've got these conditional credences. Now, suppose you're given a specification of the state of the composite system. You've got these conditional credences about the pair of preparations, and I now tell you about what preparation was done on one subsystem. Does that change your credence about what was done to the other? And if it doesn't, then I'll say that your credences satisfy the preparation uninformativeness condition. And I guess noticed that there's a typo there that should say PUC. Okay. All right. And that is that's something that is entailed by the preparation independence postulate used in the Pbr theorem, but it's strictly weaker. Even if you have a Cartesian product assumption, it is strictly weaker. Unfortunately, what I managed to get from that is a strictly weaker conclusion, not a conclusion of ontic distinction for arbitrary pure quantum states, but only any pair of quantum states that aren't too close to each other, meaning that their absolute value or inner product is less than 1 over square root 2. Now, that might be just because I don't know whether the condition actually entails ontic distinctness for arbitrary pure quantum states, and I just wasn't clever enough to be able to prove it, or if it actually doesn't. So as far as I know, that's an open question. In terms of credences, if her credences satisfy those sorts of conditions we had, the 1 through 5, and they in addition satisfy this PUC, then she should take preparations with which she associates distinct quantum states that aren't too close to each other to yield distinct physical states, conditional on theory, if theory T is true. Okay, and it would be kind of a weird theory. I mean, I don't know what kind of theory it would be, such that pure quantum states end up ontically distinct if they're not too close, but don't if they are. I actually don't know if that's satisfiable or not. Okay, which means that her credence that the preparations yield physically distinct states should be at least as high as her net credence in all such theories. So if she is dogmatic, absolutely convinced that distinct quantum states do not correspond to physical distinctions, she should provided her credences satisfy those other conditions, she'd have to have credence 0 in all such theories. Okay, so what do Cubists make of this? Right. Well, they get off the train very, very early. They don't, or actually they don't even get it. They resist the very first step, the conclusion that they should take distinguishable preparations to have ontically distinct sets. And this is not a response to, this is not a shift in their position that came about as the result of the Pbr theorem. This is something that they were saying well before Pbr published their theorem. So, if you say to Chris Fuchs, look, if Alice prepares a distinction in one of two orthogonal states, sends it to Bob, and Bob can find out about which one, well, first you say, no. Alice shouldn't use quantum mechanics to predict results of Bob's operations. She can only predict results of what she will hear later when Bob tells her what he saw. Right. Okay, fine. Right. Well, if an experiment you can do can distinguish. If Alice is certain that if there's an experiment you do that Alice believes can distinguish with certainty between two preparations, don't you think that that's mediated by an effect on the physical system? And that is something that they do not accept. Right. And at this point, you have to wonder whether they're saying these things as part of a propaganda for Cubism, or whether they really believe this. I mean, do they actually not believe? Like when Rigorshak is sitting taking notes on his laptop, does he not believe that his choice of keystrokes are distinct choices of keystrokes are going to result in distinct states of the laptop? Right? If any of you have been in email correspondence with Chris Fuchs, he's a voluminous writer of emails. Does he not believe that his choices of what to type are going to make physical distinctions in the systems that are mediating the exchange? Okay. As I said, they do appear to regard some physical systems as more suitable for the purpose of taking notes than others. And when you're buying a laptop, one of the things you ask is how much storage does it have? And what they're advertising there is how many readout distinguishable states, internal states does the thing have, right? And I've never asked them, but I suspect that they're actually willing to pay more for laptops advertised with more distinguishable internal states than others. Is there one set of rules for dealing with everyday life, and another when they put on their Cubist hats? Yeah. Okay. So what I said earlier, I'm almost out of time. I'm just going to wrap up fairly quickly. Is the argument did not at any point violate what get listed as the fundamental precepts or tenets of Cubism. So there's a short paper by Fuchs, Schack, and Merman from 2014, where they're introducing the readers to Cubism, and they present what they call the three fundamental precepts of Cubism. A measurement outcome does not pre-exist the measurement. Okay, we did not assume that it did. Outcome is created for the agent who takes the measurement action only when it enters the experience of the agent. The outcome of the measurement is that experiences do not exist prior to being experienced. I don't even know what it would mean for experiences to exist prior to being experienced, but I'm pretty sure I did not assume that they do. Now, if they mean that, if they mean, so we're not assuming that what you see on the screen pre-existed. Now, if they mean something that they're not explicitly saying, that experience isn't caused by something that pre-exists, then there's an assumption that we're violating, but they don't actually say that. An agent's assignment of probability 1 to an event expresses that agent's personal belief that the event is certain to happen. So this is actually something that we have respected throughout. It does not imply the existence of an objective mechanism that brings about the event. This is the reason why I stressed several times that if I believe that my choices of keystrokes are going to have lasting effects on the computer, I could be wrong. Right? So my belief that there's going to be a certain correlation between what I do now and what I see later could be wrong, right? So even probability one judgments are judgments. They're judgments in which the judging agent is supremely confident. Parameters that do not appear in the quantum theory and correspond to nothing in the experience of any potential agent can play no role in the interpretation of quantum mechanics. Well, actually, nothing in the argument had anything to do with interpretation of quantum mechanics. You know, these theories T that we're talking about could be any physical theory. Fuchs more recently lists 3 fundamental tenets of Cubism. There's still 3, but they're different. Born rule is a normative statement. What he means is that it's the statement that your credences should conform to some possible quantum state. All probabilities, including all quantum probabilities, are so subjective they never tell nature what to do. Quantum, right? So we've already talked about it. We're not assuming that probabilities tell nature what to do. Conclusion was about reasons from conditions on an agent's credences to conclusions about the agent's credences. Quantum measurement outcomes are just personal agents' experiences for the agent gambling on them. Yeah, so these outcomes are that appeared. They could be different states of your screen. They could be different states of your retina. They could be different personal experiences. Doesn't matter for the sake of the experience. So we haven't actually violated in the argument any of the explicit precepts or tenets of Cubism. Okay, but nonetheless, there's this sort of there's this extra condition. As I said, they resist the idea that distinguishable preparations correspond to distinct sets of the world. So they resist the very first step when I said that if your credences correspond to orthogonal quantum states, then you should regard the credences corresponding to credences conditional on a pair of preferences correspond to orthogonal quantum states. Then you should take the results of those preparations to be ontically distinct. And let's say, well, how could you not believe that? There's basically, as far as I can tell, you have to reject the idea that there's a causal relation between your choice of preparation acts today and your experience of results of readout operations tomorrow that is mediated by the effects on the physical state of the device on which you act. And there's 2 ways to do that. One is just maintain that there's a direct causal link between what I'm doing now and what I'm going to experience tomorrow, unmediated by any effect on the external world. Or reject all talks of causal links between my present actions and future decisions. And there are passages in some of Fuchs's writing that suggest the latter. So this is a passage from a paper he wrote a couple years ago. And he's been saying things like this for a while. There's a sense in which this unhinging of the Born rule from being a law of nature and the usual conception makes the Cubist notion of quantum indeterminism a far more radical variety than anything proposed in the quantum debate before. It says in the end that nature does what it wants without a mechanism underneath, or indeed any conception that would diminish the autonomy of nature's events. Nature and its parts do what they want, and we as free-willed agents do what we can get away with. Quantum theory on this account is our best means yet for hitching a ride with the universe's pervasive creativity and doing what we can to contribute to it. So the last thing does actually suggest that we have some causal effect on what the world is doing. Right. Now, is there anything? So, if I'm right, is there any reason to reject the idea that my actions today and my experience tomorrow are not mediated, but to reject the idea that they're mediated by an effect on physical systems? Well, I mean, I think that what sorts of physical laws nature does or doesn't conform to is not something that we can know a priori. if someone posits a theory according to which there are objective chances or something else that would lead one to expect certain statistical regularity, it's a theory. If you're a good Bayesian, say I can put that to empirical test according to usual Bayesian methods. I suppose that perhaps one could maybe imagine situations in which a persistent failure to find regularities of that kind might support the idea that there aren't such regularities to be found. But the actual situation is completely opposite to that. There's nothing in the way our theorizing about the world and our experiments turn out that suggests the sort of radical indeterminism. And when he says this radical indeterminism, he means not just non-deterministic laws of physics, but just no chances either. Just nature is just free to do whatever it wants, unconstrained by anything like a law. Okay, so here's the best that I can come up with. And this is going to be the end of the talk. And I honestly, for those of you who are unfamiliar with the literature, this is going to sound maybe even, uncharitable or maybe even mean-spirited. But I honestly, what I'm about to say is something that I can imagine Chris Fuchs saying. And in about a month's time, I'm going to be giving a talk like this at a conference where I think Chris is going to be the audience. And so I'd actually like to get his response. So something someone could say is that, look, I adopt this radical indeterminism, not on the basis of evidence, but as a leap of faith or an expression of temperament. Why do you take notes on a laptop? Well, even though I don't believe in a causal connection between my present acts and future experience, through psychological weakness, I can't set my credences about future experiences will, and I engage in a ritual manipulation of keyboards, pencils, etc., much in the way that someone who does not believe in a horseshoe hung above the door brings luck, because, sorry, it should be a but hangs one anyways because it makes them feel more optimistic about the future. So if that's the view, then I don't have any disagreement. If someone says that one adopts this radical indeterminism, not because of the way the experiments turned out that led people to adopt quantum mechanics, but as a leap of faith, and tells me there's no reason at all for someone to adopt it, then I'm not in any disagreement with the Cubists. Okay, so that's my talk. For the section period, I just like to leave this shameless plug up as Simon. This book is now available in the UK as of February 11th, so you can buy yours. If you're ordering from North America, it's going to start shipping on March 11th. Okay.
Wayne, thank you for that.
Thank you.
And buy the book. Thank you all. So.